This video is for Chemistry in the Earth System, Unit 2.3, Electron Representations. Today's main idea is, or essential question rather, how are valence electrons represented within a Lewis structure? Our first main idea, Lewis structures. In most elements, electrons in the outermost energy level of an atom are valence electrons. They reside in the highest occupied energy level of an atom. Many properties of an element are related to these valence electrons. Such properties include how the elements form ionic and covalent bonds. The number of valence electrons in an atom can be determined from the electron configuration of the element. The total number of electrons at the highest energy level dictates the number of valence electrons. For example, carbon, represented on the screen here, has 4 electrons in its outermost energy level. Notice the N value for the 2s and 2p sublevels are the same. They are the highest occupied energy level, whereas the 1s has a principal quantum number of 1, and it is a lower energy level. Therefore, the 2 electrons in the 2s orbital are not considered valence electrons. So, for valence electrons, we have 2 in the 2s orbital and 2 in the 2p orbital. Carbon, therefore, has 4 valence electrons. In 1916, Gilbert Lewis developed an easy method for representing atoms and their valence electrons. These simple diagrams are called Lewis structures or electron dot structures. Either name is completely acceptable. A Lewis structure includes chemical symbols for the elements surrounded by dots that represent the valence electrons. Note carbon in the middle of your screen as being represented as having 4 valence electrons, as we demonstrated on the previous slides. Lewis structures follow trends in the periodic table. For example, moving across a period from left to right, a dot is added for each additional electron in an atom of that element. Start with lithium. Notice 1 dot. Move over 1 square to the right to beryllium, and there are now 2 dots. Move over 1 more, the 3 dots. Move over 1 more, 4 dots. Then 5, then 6, then 7, then 8. And then we start it all over again with 1 dot on sodium. The number and pattern of dots are the same as you move down a group. For example, if we start with fluorine, we see 7 dots in the same pattern. As we move down to chlorine, we still see 7 dots in the same pattern. Bromine, 7 dots in the same pattern, and iodine, also with 7 dots in the same pattern. These patterns, both across a period and down a group, make Lewis structures very convenient representations of both the elements and their valence electrons. In order to draw a Lewis structure, begin by writing the atomic symbol of the element. Next, identify the number of valence electrons. The number of valence electrons will determine how many dots to use in the structure. Then, place the dots around the chemical symbol, making sure that only 1 dot is placed on each side before any of them are paired up, satisfying Hund's rule. Lewis structures can also be used to represent molecules. In molecules, valence electrons involved in covalent bonds are shown as lines. Valence electrons that are not involved in bonding, however, are still represented as dots. These dots are often referred to as lone pairs of electrons to differentiate them from bonding electrons. So here is a Lewis structure for the water molecule. Each hydrogen atom has 1 valence electron, and the oxygen atom has 6 valence electrons. Each of the hydrogen's valence electrons form a covalent bond with oxygen. These bonds are shown as straight lines. Oxygen's remaining 4 valence electrons are represented with 2 sets of dots placed on the other two sides of the chemical symbol.
But what causes elements to form compounds? And why do some elements, like the noble gases seen here in the periodic table, seldom join together? For example, neon, one of the noble gases and often used in advertising, is rarely found in a compound. For the answer to this question, we need to examine the structure of an atom and take a look at chemical bonding. Remember, each atom or molecule has a center called a nucleus containing two major particles, a proton and a neutron. While protons are positively charged, neutrons are electrically neutral. Then, whirling around the nucleus are negatively charged particles called electrons. These electrons move in paths that are arranged in energy levels. The outermost energy level is most stable when it contains 8 electrons. Whether an element is likely to bond, that is, combine with another element to form a compound, depends on the arrangement of electrons in the outermost energy level. If this outer energy level, known as the valence level, is filled with electrons, the element is chemically stable and will not bond. Chemists call the electrons in this outermost energy level valence electrons. Neon, like the other noble gases, has its full number, 8 electrons, in its outermost energy level. And because of this, all the noble gases are chemically stable.
Scientists use a dot diagram to represent the number of valence electrons in an atom's outermost energy level. Here, for example, are dot diagrams for the elements sodium and chlorine. According to the dot diagram, how many valence electrons does an atom of chlorine have? An atom of chlorine has 7 valence electrons. You can tell this by the number of dots shown in the diagram. While the noble gases have 8 valence electrons, all other elements in the periodic table have between 1 and 7 electrons in their outermost energy level. In order to fill their outer energy levels, these elements will gain, lose, or sometimes share electrons, and by doing so, form chemical bonds.
At this point, you should be able to generate a full and appropriate response to today's essential question. How are valence electrons represented within a Lewis structure?